Continuing with section 14.5, directional derivative. The directional derivative, derivative in direction u of f at a and b, is a scalar that measures the instantaneous rate of change, namely change in the value of f of x and y over the horizontal distance traveled in direction u, basically, and that's just that in instantaneous rate of change, basically. So now look at u in the domain x and y. When we talk about the derivative, the directional derivative, we're talking about the slope of the magenta up here, which is the tangent line in the direction u. And so if you look at the tangent line in direction u and u, they form a plane. So basically, if you're thinking about if we travel in direction u on that tangent line, how much y value is increasing, or z value is increasing. I'm sorry, not y value. Important, we have to remember that u must be a unit vector. Now, formula for directional derivative. Part of the derivation of the formula we haven't discussed yet, but we don't give the derivation of a chain rule in the next section explicitly neither. So let's discuss it right now. The directional derivative and derivation of the formula. So let u, the vector p and q, be a unit vector and f of x and y a differential function of two variables, and then g of t to be f of basically parameterization of the line that goes through in direction u. And so that would be f of a plus pt and b plus qt. So notice that g of t now is input is one variable, output is going to be one variable too. So it's a single variable function. Now, directional derivative in direction u of f at a and b is that limit that we discussed. It's that g of t minus g of 0 over t. Why g of 0? Plug in 0 for t in here and you get f of a and b. And so now this is g prime at 0. But also g prime at 0 is going to be, by the chain rule, equal to p times f partial of f with respect to x of a and b, and q times partial with respect to y of a and b. This kind of makes sense if you remember the Calc 1 implicit differentiation. A lot of examples we did with implicit differentiation work like that. There were different functions, part of another function, and they were related to each other, and when we took the derivative, that's how we basically worked through it. And so when I say different function, here is x and here is y, and that's what almost happened. Not quite exactly, but it gives you enough idea without seeing the entire proof, basically. And so when you rewrite this is basically p times the f sub x of a and b and q times f sub y of a and b. That is vector f sub x of a and b and f sub y of a and b dot u, which u is p and q. And so that is the formula that you need to remember. And then this f sub x of a and b and f sub y of a and b are so interesting to us. They have a special name, and we discussed that. And that's the gradient vector of f at a and b is that nabla sign It looks like an upside down triangle, basically the one vertex down, whatever upside down means, because most people draw a triangle with one vertex up, so this is one vertex down instead. So gradient of f at A and B is the vector f sub x, or a partial respect to x of f at A and B, and a partial respect to y of A and B. In terms of this notation, you want to say that d, a derivative in direction u of f at A and B, is the gradient f of f at A and B dot u.